In this video, we're going to take a look at the nature of sound waves and the speed of sound. Now, we know that sound is a longitudinal wave, and so when we think of a longitudinal wave, we can picture a pulse traveling along a slinky. And so we have a little compression that travels along the slinky. Well, the sound wave acts the same way, except instead of having a compressed piece of metal that travels down a slinky, it is a compression or a condensation of air or some type of medium through which it propagates. In most cases, sound is traveling through air, so we'll think of the example here as condensing air. So we get a little condensation of air, and then that travels through the normal air pressure, and when it moves forward in this normal air pressure, it leaves behind it a temporary vacuum of sorts, which then creates this rarefaction. And so that's a less condensed piece of air as compared to the normal air pressure. So we have this condensation piece that moves to the right through the normal air pressure, and then it leaves a rarefaction behind it. Now, if that's just one pulse, then we only see the one pulse that goes across. However, typically with sound, it's a periodic wave, and so we get more and more pulses that happen every instant, and so those continue to send out these pulses. In a periodic wave, the distance between these pulses we call the wavelength, and we know this is just like in a transverse wave, crest to crest gives us the wavelength, or trough to trough. Well, in a longitudinal wave, it's the same, but we're going from compression or condensation to compression or condensation, or we can look from rarefaction to rarefaction. Now, it's a little more difficult to look from rarefaction to rarefaction because it's harder to see the actual trough in that case. It's typically easier to see the condensation or the compressed piece. As sound propagates, as pictured here from a speaker, it is not actually moving air, individual air molecules from the speaker to your ear. It's not a flow of air. Think of this is a wave, a vibrational wave, not a flowing river of air particles. Okay, it's not like a stream of air or a wind. Okay, it's a little different. We're vibrating the air molecules. So the speaker vibrates the air molecules next to it, and then those air molecules interact with the air molecules next to them. And so the vibration is propagated from one pocket of air to another pocket of air, 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 until it reaches your ear, where that pocket of air that's vibrating vibrates your eardrum and then sends the electrical pulses to your brain through the auditory nerve. And so the key here is that we aren't moving an individual air particle from the speaker to your ear. We're vibrating those particles, and then that vibration cascades down and propagates the wave. Another thing to point out here is the wave front. Now, the wave front is curved as it comes out of the cone, partly because this surface, the diaphragm of this speaker, is curved, but then that continues to bend out, and we see that the opening of this arc gets bigger. The arc length gets bigger, but the opening actually stays the same. It's the same angle that we have here. And so someone standing inside of this arc would be able to hear the sound, whereas someone standing out here would not be able to hear it. Now, that's assuming that there's nothing over in this area for the sound to bounce off of, but if we were in a truly open field and we had a speaker, we stand on the edge of the wavefront, we would not be able to hear the sound. Since sound waves are periodic, they have a frequency, and we know the frequency is the number of cycles per second. Well, how does our brain translate the frequency? Well, we translate that frequency as pitch. So higher frequency we perceive as a higher pitch. And so lower frequency we would perceive as a lower pitch. A sound with just a single frequency we call a pure tone. Now, typically, most sounds that we hear are complex. Even sounds from an instrument are going to be complex. There are going to be several frequencies and several waveforms superimposed on top of each other. However, if we have, say, a tuning fork or just a single tone, that will be of one frequency. Now, with sound, we can change the loudness or softness. Now, the attribute of the wave that is changing when we're doing this is the amplitude of the wave, or the amount of pressure we have in the highs and the lows. And so that condensation pressure is going to be much higher if we want to make it louder than a softer noise. And so the key here is that loudness is attributed to the amplitude of the pressure wave. As sound travels through different objects, its speed changes. And the speed at which sound can propagate is actually dependent upon the medium through which it propagates and some of the conditions about that medium. For instance, air, as the temperature changes, we do see a slight change in the speed of sound. Now, this is assuming that we're keeping all the other variables such as pressure and humidity constant. Those monkey with it a bit as well. However, as temperature increases, we increase about 6/10 of a meter per second per degree Celsius. Now, that typically only works, that rule of 6/10 of a meter per second per degree calculus, that typically only works between 0 and 100 degrees Celsius. And yes, I know I just said degree calculus. I meant Celsius, but you know what I mean. So if we go from 0 to 100, we can use that rule of thumb for every degree Celsius that we increase. We're going to increase 6/10 of a meter per second for the speed of sound. And looking at some other gases, we see that just pure carbon dioxide, we are actually traveling much more slowly than typically in air. And in helium, we travel much more quickly. This right here is why when you breathe in helium in your lungs, you start to sound like a chipmunk. Okay, your voice gets much higher because when you ingest the helium into your lungs, the air coming out of your lungs, sound is coming out much more quicker than in the normal air because sound travels more quickly through helium than it does the regular air. And so if the speed is increased, the wavelength is still the same because your vocal cords aren't changing. And so we perceive that as a higher frequency, and we hear a higher frequency, higher pitch. As the helium reaches equilibrium with the air, we start to hear our voice go back down to normal. And as you can see, general rule, liquids, sound is much faster, and solids, sound is even faster still. So we can use this idea to bring up this conceptual example that maybe you've heard before in a thunderstorm. So there's a rule of thumb for estimating how far away a thunderstorm is. And after you see a flash of lightning, you can count off the seconds until the thunder is heard. And if you divide this number of seconds by 5, the result gives you the approximate distance in miles to the thunderstorm. And so the question is, why does this work? Well, in order to understand why this works, we have to look at the difference between the speed of light and the speed of sound. And 1 mile is about 1,600 meters, so it's about 1,600 meters. And so the speed of light, we know that travels at 3 times 10 to the 8th meters per second. The speed of sound, well, this is a summer day, thunderstorm, maybe it's 350 meters per second. And so if you look at that, well, the 3 times 10 to the 8th and 3 times 10 to the second, well, really, the difference between those two is pretty darn close to just 3 times 10 to the 8th because, the 350 is insignificant to 300 million. So looking at that, well, we look at, well, how long does it take light to travel just 1 mile? And so if we take the 1.6 times 10 to the third divided by the speed of light, or just under the speed of light, we get about 5 seconds. So every 5 seconds, light is traveling 1 more mile than the sound is. So that's why we can count how many seconds between, divide by 5, and we can get the number of miles it is away. The last relationship here we're going to look at is looking at the speed of sound through different objects. And so when we look at liquids, or we look even at solid bars, we see that the elastic deformation constants come out. remember the stress and strain ratios, and we had the bulk modulus, the Young's modulus, and the shear modulus. Well, we're ignoring the shear modulus because that really does nothing here. But it does, the bulk modulus does come into play here when we're talking about liquids. The speed at which sound will travel through a solid can be found by taking the square root of the ratio of the bulk modulus to the density of the object. And that's kind of profound there, in that, we're looking at these two attributes of an object, the bulk modulus, how elastic it is, and the density, how dense it is, how close we have these molecules packed together. And if we divide those two and take the square root, that gives us the speed of sound. And that's kind of amazing. And the same thing happens when we're looking at solid bars or wires even. And we just look at the Young's modulus divided by the density and take the square root. And so what this tells us is, it tells us, all right, the more elastic a substance is, meaning the higher the bulk modulus is, um, or I guess I should use a better adjective, the more resistive to elastic deformation an object is. So the higher the bulk modulus, the more resistive it is to compression or expansion, then it's going to have a higher speed of sound that travels through it. But also, we got to keep in mind that a lot of times when the bulk modulus increases, well, so does the density, and that's not always the case, but that may come into play here. And so we got to understand that there's an inverse relationship to density as well.